Good morning, all of you. In the last lecture, we have discussed about the parallel plate conducting plates having the small distance d with the vacuum as an dielectric. So, in that explanation, we have discussed about how the vacuum it should be works as an dielectric material, and according to that, the electrical field which should be stored in that capacitor with the formula E is equal to V upon D. According to that, the charge accumulated on each plate, it is also calculated by considering the Q0, that should be nothing but the charge at initial site is directly proportional to the applied voltage V. The charge produced by that each plate of capacitor is equal to the capacitance, initial capacitance of that capacitor multiplied by the voltage applied on that capacitor. So this is how the vacuum should be produces the output equations. Also, we have discussed about the electrical flux density within the parallel plates is given by capital D is equal to Q0 upon A. According to that, the field intensity E becomes Q0 upon epsilon 0 into A, and the final charge equation of the parallel plate capacitor with vacuum as an dielectric is becomes Q0 is equal to epsilon 0 into A divided by small d multiplied by V. Now the Q0 should be nothing but the charge stored on that capacitor. Epsilon 0 is nothing but the permittivity of that dielectric material, that should be nothing but the vacuum. A, it is nothing but the area of that conducting plates. Small d is equal to the distance between the two plates, whereas capital V indicates the voltage which should be applied on that capacitor. So up to this point we have discussed about the vacuum as an dielectric material with parallel plate capacitor. Now the next point is that the parallel plate capacitor with solid dielectric. Over here the two diagrams, it should be shows that what is the difference between the vacuum as an dielectric material and the solid dielectric material when we can place inside that parallel plates, then how the capacitor it should be behaves. In this diagram, the positive charge Q, it should be along with the parallel plate with dielectric material, and the negative charge is stored on one side of that capacitor with parallel plate capacitor. Now when a dielectric material it should be placed between these two, then how the charge and the capacitance it should be changes. We have discussed this point with respect to the equations as well as the explanation of that dielectric material. Now let there be two parallel plane conducting plates, each having a area of capital A square meters, be separated by a small distance small d in a dielectric material. The potential difference between the plates is kept constant at V volts. Then it is observed that the charge on each plate increases to a new value Q from Q0, and the Q is given by the following expression, that is nothing but Q is equal to C into V, where the new capacitance C is higher in a value than C0, and it is given by C is equal to epsilon A upon D, where epsilon is equal to absolute permittivity of the dielectric. Now, if we can take the ratio of C upon C0 is equal to epsilon A upon D divided by epsilon 0 A upon D. Now, if we can solve this example or this equation, we can get C upon C0 is equal to epsilon upon epsilon 0. Now, the ratio of epsilon upon epsilon 0 is called as relative permittivity or specific inductive capacity or the dielectric constant of the material, and it is denoted by epsilon r, and it is a unitless quantity where epsilon r is equal to epsilon upon epsilon 0. Now, what is the major difference between this concept and the previous concept is that when we can apply a voltage over here, the charge produced in that dielectric material, it should be changes from Q0 to Q value. Now Q, it is the new generated value with a solid dielectric material. Q, it is the new value which should be generated when a solid dielectric material is placed between the two capacitors. Now that charge Q value is we can define Q is nothing but C into V. Now the new capacitance C is the new value other than C0. Now C0, it is the value of capacitance when vacuum dielectric material is to be considered, so that the C value, it is the new value when a dielectric material it is to be placed between the two parallel plate capacitors. Now we have to be discussed or we have to be assumed that the C is equal to epsilon A upon D, the standard formula for capacitor, that is nothing but the capacitance is equal to permittivity multiplied by area of that conducting plates divided by the distance between the two parallel plate capacitor, that is nothing but D. Now if we can take the capacitance value at solid dielectric divided by the capacitance value at vacuum dielectric, then we can get the equation of C upon C0 is equal to epsilon A upon D divided by epsilon 0 A upon D, and when we can solve this equation we can get the new term in this dielectric concept, that is the relative permittivity, which is also called as the dielectric constant of the dielectric material, and it should be denoted by epsilon r. Now how the epsilon r should be getted? The epsilon r is equal to epsilon upon epsilon 0, epsilon upon epsilon 0. Now there are, along with these two concepts, we have to be conclude these three factors which are directly affect the capacitance value. Okay, these are the three factors which are affects the capacitance value. In this slide, we have discussed that part. Now, the capacitance C, it should be depends upon three factors as follows. The first one is nothing but C is, that means capacitance is directly proportional to area of the plates. Capacitance is directly proportional to the area of plates. Means if the area of plates goes on increasing level, then the value of that capacitance is also goes on increasing level. The second parameter is that the C is directly proportional to the dielectric constant epsilon r of the dielectric material. C is means capacitance is directly proportional to dielectric constant epsilon r of the dielectric material. Means if the epsilon r value goes on increasing level, then the value of that capacitor should be goes on increases, and when the value of epsilon r is goes on decreasing level, then the value of C is also goes to decreasing level. Okay, and third, the capacitance is inversely proportional to the distance d between the two plates. The value of that capacitance is inversely proportional to the distance d between the two conducting plates. Means if the distance between the two parallel plate capacitor goes on increasing level, then the capacitance value goes on decreasing, and when the distance between two parallel plate capacitor goes on increasing level, then the value of capacitance should be decreases, and when distance between the two plates goes on decreasing level, then the value of that capacitor goes on increasing. So over here the capacitance is inversely proportional to distance small d. Okay, so the value of that capacitor, it should be depends upon mainly three parameters. The first one, that is area of that plates. Second one, that is epsilon r, we can known as a dielectric constant of that material, and the third one should be nothing but the distance between two plates where the capacitance is inversely proportional to the parallel plates. The next point is the electric dipoles. Now the electric dipoles, it is the phenomenon when we can apply a electrical field towards an capacitor. Okay, let's check what is that phenomenon. Now upon an application of DC or static electrical field, there is a long range migration of charges. However, there is a limited movement of charges, leading to the formation of charge dipoles, and the material in this state is considered as polarized. These dipoles are aligned in the direction of applied field. The net effect is called polarization of the material. A dielectric supports charge by acquiring a polarization in an electrical field, whereby one surface develops a net positive charge while the opposite surface develops a net negative charge. This is made possible by the presence of electrical dipoles, two opposite charges separated by a certain distance on a microscopic scale. Okay, so in this slide we have discussed regarding with the electrical dipoles. Let's to be understand this one. Okay, now when we can apply a electrical field, either it should be a DC or a static, to a capacitor, then there should be a long range migration of charges between that capacitor. In a dielectric material, the charges of that electrical field, it should be transferred from one end to the another end. Now during that migration, the limited movement of charges leading to the formation of charge dipoles. Now what is meant by charge dipoles? The charge dipoles is nothing but it is an state where all the negative side charge placed at one end of capacitor, whereas all the negative sided charge it should be placed on another side of capacitor. Now the position or the situation of that capacitor where one end it should be considered as a positive and another end it should be considered as a negative, that situation should be called as polarization of the material. That situation should be called as polarization of the material. Now when a dielectric supports that charge by acquiring polarization in an electrical field, one surface it should be developed net positive charge, while another it should be developed net negative charge, and that concept or that situation, that phenomenon, we can call as, this situation should be called as electrical dipoles. Dipoles is nothing but di means two, poles means the states or the stations. Okay, now the two stations or two positions, when it should be occurs, when all the negative charges should be placed at one end and all the positive charges is kept at another end. Okay, should be called as electrical dipoles. So over here, when we can call as capacitor is at electrical dipole situation, when the polarization it should be occurs, then the charge it should be separates at a particular distance r. Okay, where a positive charge it should be considered as a left hand side and the negative charge is at the right hand side with a particular distance, a small r. Then we can call as, this situation we can call as electrical dipoles. Okay, let us suppose over here the one end should be present, we can call as a net positive charge or net positive end, and over here the net negative end or net negative charge should be present. Such a situation should be called as electrical dipoles, which are separated with a small distance, small r. Okay, now this is the situation where the electrical dipoles or polarization concept it should be there. Okay, now you can see the structure of that particular charge atoms where cation and anion is placed over here. Now the anion and cation should be generated with anode and cathode. Okay, anode and cathode is shown over here. Now the electrical dipole mu is equal to q into r. Now Q, it is nothing but the charge which is placed on that particular material. Okay, the charge on that particular ion. Okay, when we can consider, let us suppose in this diagram we have to check that concept. Let us consider this ion, it should be having over here the first state with or before the applying electrical field, before applying electrical field. But when electrical field is should be applied over here, that charge it should be changes its state, and it should be travels towards an anode, anion, or towards an cathode with small distance, that is nothing but capital R. Now the charge it should be itself contains a negative charge, whereas cation it should be considered as a positive charge. Now such a situation where the cation and anion should be having a small distance r with a positive charge and negative charge, then the situation should be called as a polarization, and the structure of that two ions should be called as electrical dipoles. If the center of a positive charge within a given region and the center of negative charge within the same region are not in the same position, a dipole moment mu should be arises. For example, in the diagram, the center of positive charge from the 8 cations shown in at x, while the center of negative charge is located some distance away in the anion. And that's why we can call as the moment of charge in that dielectric material should be creates the distance small r, where one positive charge should be present, one negative charge should be present, and in between them some distance should be maintained. That situation we can call as electrical dipoles. That situation we can call as electrical dipoles, and the structure of that atom should be called as polarization. Polarization of that material. Okay, so this is how the electrical dipoles are to be works. Now the next point is that the frequency dependence of electronic polarizability. In that one, the first one, what is meant by polarizability? When an electrical field is applied to a material with dielectrics, the positive charge are displaced opposite to the direction of field and negative charge displaced in the direction of that field. Now, the displacement of these two charges create a local dipole. Creation of dipole by applying an electrical field is called as polarization. Creation of a dipole by applying electrical field is called as polarization. Now, the polarization is defined as induced dipole moment per unit volume. Polarization is defined as induced dipole moment per unit volume. That should be nothing but P is equal to mu upon volume. P is equal to polarization is equal to mu upon volume. Okay. Now, how the frequency should be depends upon polarizability. We have to be checked. Okay. The frequency dependence of electronic polarizability. Before starting with that example, we know that the refractive index of a material depends upon the wavelength of light. This phenomenon is called as dispersion. We can know as that is nothing but dispersion. Now, it is assumed that the electrons in an atom are vibrating naturally at some frequency which is differ from different materials. If we apply an electrical field, that should be nothing but external electrical field, then electrons are set into focused vibrations. The molecules in a dielectric material are represented as dipoles or bound charges. Therefore, the number of positive charges should be equal to the number of negative charges to maintain the dielectric material electrically neutral. Okay, and so that on application of electrical field, the polarization process occurs as a function of a time. The polarization P of t as a function of time. The phenomenon P of t now the polarization it should be given as P of t as a function of time. The P of t is further described as P of t is equal to P in bracket 1 minus exponential of minus t upon Pr bracket completed, where P is equal to maximum polarization attained on prolonged application of the static field, and Tr is nothing but the relaxation time for particular polarization process. The relaxation time Tr is a time measure of the time scale of polarization process. It is the time taken for polarization process to reach 0.663 of the maximum value. Electronic polarization is extremely rapid even when so this is how the frequency dependence on electronic polarizability should work. Now the ionic polarization is due to the displacement of ions over a small distance due to the applied field. Since the ions are heavier than electronic cloud, the time taken for displacement is larger. The frequency with which ions are displaced is of the same order as the lattice vibration frequency. It is approximately equal to 1013 Hz. Hence, at optimal frequencies, there is no ionic polarization. If the frequency of applied voltage is less than 1013 Hz, the ions respond. Orientation polarization is even slower than ionic polarization. The relaxation time for orientation polarization in a liquid is less than that in a solid. Orientation polarization occurs when the frequency of applied voltage is in audio range. That should be nothing but 1010 Hz. The space charge polarization is the slowest process as it involves the diffusion of ions over several interatomic distances. The relaxation time for this process is related to the frequency of ions under the influence of applied field. Space charge polarization occurs at power frequencies that should be nothing but 50 to 60 Hz. So this is how the frequency dependence of electronic polarizability should be works. Now the figure shows the real part as well as the imaginary part of electronic polarizability. Okay, when the real part is 0, the imaginary part has maximum positive value. Means when at a particular frequencies, that should be nothing but the power frequencies, the polarization is having a higher value. Also note that in the region of resonant frequency, the real part has a positive maximum and a negative maximum. In a practice, an atom contains multiple electrons, each one having a different resonant frequency with various frequencies range. That should be nothing but a power frequency, audio frequency, radio frequency, infrared frequency, or optical visible frequency. Now, the polarization it is also goes on increasing level either by electronic, ionic, orientation, and space charge polarization. In this diagram, we have discussed that one. When the power frequencies is to be considered, we can get the highest level of polarization, and when we can comes from power to optical visible frequencies, the polarization level goes on a decreasing level up to the electronic polarization is the lowest type of polarization should be occurs with optical visible frequency. Optical visible frequencies. Okay, so over here in the x-axis the frequency parameter should be shown. In the y-axis the polarization parameter should be shown. Okay, the frequencies are further classified according to the power frequency, audio frequency, radio frequency, infrared, and optical visible. Whereas the y-axis it should be classified according to the electronic, ionic, orientation, and space charge polarization. Okay, so we can conclude that the frequency dependent of electronic polarizability is having the maximum polarizations only when the electrical frequencies are to be applied on that one. That should be nothing but power, audio, radio, and some part of infrared. Okay, between this range, that is electrical frequencies, we can get the maximum or moderate polarizations of that capacitor. Okay, so over here we can conclude this part. If you have any query regarding with this topic or this unit, should be definitely asked to me. Okay, thank you. We can conclude over here. The remaining part it should be taken in the next lecture.